second second event from the Warsaw.ai series. Today is the first time when we meet in Przestrzeń from Facebook, so we would like to thank our host, and we would also like to thank our great sponsors. Today's event is sponsored by deepsense.ai, so thank you once again for supporting us. For today we have in plan 3 interesting talks given by our great speakers. The first will be Paweł Godula from deepsense.ai, representative of a sponsor. The second will be Zbigniew Wojna from Tensorflight. And the third, Paszke, PyTorch, University of Warsaw. And then we'll have a closing speech and food and networking, so small after party, a bit more modest than usually, because I guess that all of you are aware of the tragedy which happened in Gdańsk a few days ago. So we decided that we would also like to commemorate the president and to give a honor and to respect to the mourning which was introduced in Warsaw, and our solidarity against violence. So please stand up for a minute on silence. Okay, thank you very much. So we can start. The first presentation will be given by Paweł Godula from deepsense.ai. Paweł, the floor is yours.
I think I didn't need the mic. Do you hear me back then? Yes. Can you hear me well? That's okay? Okay. Just give us a second to... Okay, very nice. Okay, so hello everyone. Thank you for coming. My name is Paweł Godula. I work at deepsense.ai. And first of all, I would like to really thank the organizers for inviting me for this talk. I think you have gathered really a great community here. It's very good to have a place where we can share experience between people who actually do AI instead of only talking about AI. So I think it's a really great initiative, so keep it up. And plan for today is there are 3 steps in these 20 minutes that I have. First is to discuss a little bit about case studies where we use AI. We at DeepSense we work in technology projects for many clients, and we focus on building custom-made AI systems for our clients. And today I would like to share with you a little bit of experience from these projects. Then I would like to show you a very concrete example of how we can use AI to enable feature extraction from the data coming from different streams, because this is really hot topic for us now. And then based on this case, I would like to discuss with you a little bit or where is the place where AI can actually bring the highest value today. Okay. So we work a lot with retail companies and banks, and I have put down several questions that in 2018 were the most popular. Deployment. So for example, what are those questions? What is the chance that the customer will buy our product? What is the probability that the customer will fail to repay a loan? Which exact product should we offer to the customer? Is it likely that a customer will unsubscribe from our service within the next 6 months? What is the predicted value of a customer over the next 1 year? Or should we use email, Facebook, or Google to contact the customer with our offer? Of course there are more, But these 6 questions, they come up very often, and they have a very high commercial value to our clients. These are the questions that they are really interested in answering, because if they can do it, then they can earn more money, quite simply. And there is one unifying theme of all these questions that I would like to talk about today, and this theme is basically how to find traces in the digital data that customer is leaving in our company, and how these traces can help us answer these questions. And in machine learning, this problem is often called feature engineering. So how to transform the raw data that the customer is leaving with our company to data that is actually that can be used by the model. And we know, and it has proven time and time again on our project, that for us, actually the data question is much more important than the algorithm question. To me, it's really astonishing how neural networks have captured the imagination not only of academia, but also of business people. So whenever we talk about these kind of projects, we get a question, are you going to use neural networks on our project? Are you going, more horrifying, are you going to use TensorFlow? And for us, it's a little bit, more often than not, we answer, this is not the most important question for this project. The more important is actually which data are we going to use to answer this question. And I give you that. There are several domains where it all started, the image analysis, then the text analysis, then the voice and speech analysis, where neural networks have completely revolutionized the field. But for these questions, actually, if an old friend, logistic regression, that does not help us answer these questions, the solution to the problem is actually not to throw neural networks at them. It's actually more to think about the formulation of the problem, about what data can we bring in to answer these questions. So having said that, the feature engineering is central to answering these questions. That is coming from our experience so far. And what kind of data we have at disposal? So for example, this is the example from e-commerce company. We have historical transactions of a customer. We have his behavior on the website. We have his behavior in the app. We have his emails sent to the service desk. We have his response to the newsletter, and also some other external data, for example, his behavior on social media. However, to be honest with you, the external data rarely adds value to our project. It's very difficult to use external data to a good degree on a project. And the only one case where I had a chance to use external data with a good outcome was where we were forecasting demand for anti-flu drugs. These are highly seasonal drugs, and external data which you can find, for example, in Google Trends, especially where people type in. So where we are forecasting these seasonal drugs, there is actually very interesting data that you can use, is actually the popularity of the phrase, how to cure a flu, in Google. And actually, how many people type this phrase, how to cure a flu, or what is the best anti-flu medicine, is actually very well correlated with the outbreaks of flu in Poland. We have checked the data from Państwowy Zakład Higieny, and it turned out that Google knows 3 weeks before Państwowy Zakład Higieny that the outbreak of flu is coming in Poland, because of the self-diagnosis, and because this data is immediately available. So this was the only, and this data is available in Google Trends. So this was the one case where actually the external data was relevant. In other cases, we find it very hard to use it. And then first step is actually to have all these sources in one place, linked by one customer ID. This is what we call on a project a single source of truth about the customer. Then the second step is extracting the features from all the sources separately. And then the most advanced kind of state is being able to explore interactions between signals coming from different streams. And to be very concrete, what I mean by all these steps, I will give you an example coming from our favorite Kaggle competition. Who knows Kaggle? Okay, so we have a very high, who doesn't know Kaggle? No one.
Actually, it's the first time ever that I have a talk, and everyone knows Kaggle. So I don't have to explain what is it about. And there was a Kaggle competition called Home Credit competition. Who, I don't know, participated or had a look on this competition? Not so many people. Okay, so I will explain what the competition was about. The competition was organized by a home credit bank. The bank it was founded in Czech Republic, and the business model of this bank is to give loans to the people who are at the border of their financial standing, meaning that people who cannot get a credit anywhere else, they go to home credit and get their credit. Of course, they need to pay higher interest rate for that. So if you think about this business model, which is basically giving loans to risky clients and extracting a premium from them, the accuracy of the model predicting the default on the loans is actually one of the most critical elements of this business model, because whether you are able to differentiate good clients from bad clients is actually very important for your probability, even more so than in normal bank. Even also in normal bank it is important. So what data in this, I'm revealing this example because this is a non-confidential example that we can share, and the technology that we used here to analyze the signal coming from different sources is actually based on AI, neural networks, that I will show in a minute. And we think is actually one of the most interesting applications of neural networks right now, at least for us. Okay, so what kind of data we had? We had the data about the loan itself. So what is the amount of the loan? What was the objective of the loan? We also had the data about a customer, about his previous loans with home credit. And also we have a data about the customer coming from external credit bureaus. So not only by the home credit bank, but the data coming probably from other banks and stored in some kind of central bureau, which is gathering the data about all customers taking a loan. And we had a historical data about 300,000 customers, and the objective was to train model on this 300,000 and then predict the defaults for the next 50,000 customers. And how we started this project, it is actually very similar to how we start working on commercial projects, is the manual feature engineering. So there was a team of 3 of us, and we sat in a room and long brainstorming, thinking, and we basically came up with more than 10,000 features, out of which 2,000 features proved relevant. And some of the most powerful features were the following. Of course, if a customer has already defaulted on previous loans, he is very likely to default on future loans. And default on a loan means fail to repay a loan. So previous defaults were very important, but especially it was very important the amount of the problem, the size of the problem basically. So if more than 30% of installment was missing for more than 45 days, and especially if it occurred within the last 3 years. I'm putting so many details about these repayments because it will be helpful later on to explain why neural networks are so good for this task. These numbers, what is the percentage of installment, or how many days, or what is the time horizon, we all determined by cross-validation. And then another very interesting feature was rejection by external credit bureaus. So if someone was rejected by external credit bureau, it was also a very powerful feature telling us that someone probably will not repay a loan. And then there was a very interesting feature, extreme values in the credit to goods ratio. So if you think about what kind of loans we are talking about here, we are talking about cash loans and installment loans. For example, the loans that you are taking to buy a TV. And if you think about possible values of a loan to buy a TV, there is a certain range of values that you are expecting. If someone is telling you, okay, I want this loan to buy a TV, and the value of a loan is either very large or very small for a given objective, it means, well, that maybe this customer is not telling you his true objective for this loan. And this is a very powerful feature to distinguish good customers from bad customers. But after maybe it was probably a month of brainstorming, we were really exhausted and we couldn't come up with more features. We were almost, like we hated this data already. So we thought, okay, maybe let's think about something more intelligent. And the key data property in this case was that we had different streams of data about the customer. So each previous loan of a customer may be treated as one stream of data because it is generating on a monthly basis the information whether someone was repaying on a given time or not. Also, the data from external credit bureaus can be treated as a separate stream. And because you have also the time dimension, the possible combinations of human behavior is almost impossible to guess. Like, think about the feature 3 years ago, someone applied for a credit at external credit bureau, was rejected, and then 2 months later, he applied for a loan at our bank. This is clearly some behavior indicating that someone is, maybe not getting a loan somewhere else, but then he's trying to substitute this other source with our bank. But this kind of behavior is really difficult to guess a priori. So what we did, maybe we thought, maybe let's use technology for us to figure out this kind of behaviors. So what we did, I will go straight to the meat. What we did, we built a user image. What is the user image? User image is basically raw data transformed in such a way that on a horizontal axis you have 96 months, which means that we looked for 8 years in the past. We basically analyzed 8 years of a client history. And in rows, you have his different streams, raw data streams. So for example, you have account inflows, account outflows, number of installments due, number of installments overdue. These are internal data sources. You have also external data streams, like applied for loans in other bank, and this is a flag. Got rejected by other banks, and this is also a flag. Of course, if you build, what we basically did, we have built this user image, and then we basically let the neural networks figure out what kind of behavior are leading to a default or not. So we have built a one-dimensional convolutional layer, which was sweeping basically through time. And then this layer was in order to extract features, and then we had a bidirectional long short-term memory layer, and then already a default. As you can see, it's a very simple. Well, it's judgmental. It's a quite simple architecture. The key is basically enabling each filter to look at 2 months of behavior and basically figuring out the interactions between behaviors coming from different channels. Of course, this user picture is before normalization because, as you may imagine, it's really difficult to train neural networks on this because you have one row taking values between 0 and 10 million, and the other row which is taking values which can be only 0 or 1. So for neural networks, it's really difficult to train this kind of network, but it can be done with good normalization and standardization of input data before feeding it to the network. And actually, this architecture let us figure out the features and client behaviors that we were not able to figure out only in our using our human brains. And it added a lot of value and information to our main model, which was gradient boosted trees model. And thanks to this, we finished on 5th place out of 7,200 teams. It was the largest Kaggle competition so far. And maybe one additional comment. I see my time is coming to an end, but just one additional comment. We believe this technology of building a user image is very universal, because actually, if this is default on a credit of this is, for example, purchasing a particular product, it is not so much relevant. Building the user image and actually putting all the different data streams together in the structure, we believe this is a really nice way to represent human behavior, and this is one way to let neural networks do the feature engineering for us. And we are really exploring this technology on projects in e-commerce and in banks that we are doing now. Okay, thank you so much. Now I believe is the time for questions.
Let's thank Paweł for a great talk. Okay, questions?
So 10,000 features in the beginning, like each single feature was thought before, or you generated some automatically?
Of course, I think we have generated around probably 1,000, let's say, or maybe couple of hundred of. We have generated couple of hundred of distinct ideas, and then by multiplying by the time, for example, all different aggregations, we came with 10,000. Of course, 10,000 is not all of them are like single ideas. I think we have a couple of hundred ideas that we tested.
Okay. More questions?
And so you have mentioned that you use this neural net in order to choose more features. So can you elaborate on how this process actually took place?
So we tested two ways to add features from this model to the gradient boosted trees model. One way was to take out-of-fault predictions from the penultimate layer and then feed them to the model. And the other way was to basically take out-of-fault predictions from the ultimate layer. So the ultimate, basically, the out-of-fault predictions, basically. And we tested these two ways to add them to the model. But also we explored the filters, because the most interesting, at least for us, were what the filters would learn at this point. And the example that I gave you before, that someone got rejected by our bank and then he applied for, got rejected by other banks and then he applied for a loan at our bank, it came directly from the interpretation of one of the filters, if I remember correctly.
Okay, thanks. We have time for one more question.
Hi, thanks. You mentioned you added the features extracted from that model to gradient boosting model. What was the performance of that model on its own?
It was very weak performance. It was very weak. It was almost like unimaginably weak. It was only because we estimated that there was too many parameters in the model compared to the amount of signal that we had. And also for this reason, as you can see, the filters are only 2 months filters. We also tried, for example, to have one filter look at 5 months, for example, but then the number of parameters really was too much, and the filters were not really learning. Of course, they were to some point, but they were it was weaker. The model itself had, I think, like area under curve around 0.7, and then the kind of the gradient boosted, the final gradient boosted model had area under curve around 0.82, something around this. So this model on its own was weak, but the ability, it was its ability to kind of extract these behaviors that added to our main model.
Okay, thank you. We don't have time for more questions now, but you'll have opportunity to ask your questions later during the networking part. So thank you once. Let's thank once again Paweł. Okay, and now our second speaker, Zbigniew Wojna.
Okay, hello, thank you. Thank you for being here. Thank you to organizers for inviting me to present a little bit about object detection during today's talk. Myself, I'm doing PhD at University College London, and I'm running the company Tensorflight Inc. We have a few friends from Tensorflight here, so you can also catch up with them later. I usually start my talk with like small joke. It can be funny for some of you, maybe not. Like how the history of neural network progressed. So in 60s, we had like this simple model of perceptron, and yes, we were able to recognize between sexes, between male and female, with such a simple model. Just input, weighted input with respect to like different pixels, and then stepwise function. And if it's above 0, that means it's woman, and below it's man, or other ways around. 20 years later, we found out that actually maybe we can replace the stepwise function by sigmoidal. We will do backpropagation because now we can update all the parameters in single pass, and it's much faster to learn. So that was woohoo moment, and now in 2000 we actually replace it with ReLU, and we see that actually very deep neural networks now can be trained because the backpropagation doesn't vanish. So that's end of the joke. Okay. Problems. So I will describe today the recent advances in object detection. Here recognition, it's very well-known problem. You have ImageNet dataset or like any other dataset that have like objects. You want to recognize what is on the object. Localization, initially in ImageNet, it was just one object in the ImageNet dataset, and we wanted to like draw the boundaries around the object. Detection is different from that way defined localization. With detection, we want to find all the objects that are on the image and be able to like draw boxes around them. So the third picture shows the detection. So here we see like two dogs, sorry, dog and cat, like kind of follow-up problem when we try to extend it is to actually look holistically on the image and try to understand every pixel, like to what type of class it belongs. And naturally, you also, in this case, may need to do detection of every object. Here it may be simple because you may not have to recognize between different instances. But if you have to recognize between different instances, then you must be also able to like draw box around every of these. And if we like grow the set of applications, actually almost infinite, we can like try to recognize more and more details in all these images. And this is like work from the last year. So we can see that like, okay, if we want to recognize object, it's maybe just a bit simpler. But if we want to start like draw details and understand like every element, we have to have like this framework of detection to be able to reason about every of the found objects. So we have to find them first. And there is a lot of problems that requires detection. So to give you some like comparison why that may not be as easy. So that's like also a simple joke, but usually funny. Try to find, if you have like problem before, try to find the person now. Actually, it's quite difficult. It's here. So it's actually, this is like very tough example, but if you think about like all the prevalence of object detection problems in the self-driving cars or like medical imaging, where like you will naturally aim to make this fully automated, we have to be able to solve as easy problem as this one. And we actually right now in kind of the age of like really growing the expertise in object detection. So if it comes to like recognition, we plateau. So from 2015, we see that like there is less and less progress. But if we look at what was happening in the detection, we see progress up to 2016. And here I like capture one of the like borrowed one of the slides. We still see up to 2017 that we're still really growing in the performance. And this is a little bit fake because actually this network with 36 MAP does very heavy inference, which means they do maybe 40 times inference on the same image to actually really improve the results. So I would say in the last 2 years and probably like next 2, we will still see like the new models that are faster and better. Probably that will plateau also in like 2-3 years. So now I have like a set of slides that I was actually presenting during PL in ML. It was like review of last 10 years. But today, but today I wanted to focus on the current advances, what was happening in the last year, and like what we see as a potential new progress. So this is like system output from mask RCNN. So you can see that actually most of the objects of small objects are missed, even if they are like in very simple situation on the road, or especially with many birds, you could have context that, okay, there is a sky, but still like systems are not able to manage that. And I think the community realized it to some extent. So this is actually some analysis that we did in Tensorflight. We tried to tackle small object detection. I would say we didn't have too much luck with that. I think there are like other works that did it much better. So if you look at the COCO dataset, you can see that like small objects consist of like they form quite large part of the whole dataset. There is like 41% of small objects, and small means like less than 32 by 32 pixels. So it's relatively small. And like total object area in the whole dataset is less than 1%. So now you have to learn your model to find something that consists of like less than 1%, and at the same time learn objects that like consist of 88% of the image, like large ones. And at least the way we try to do this is by some sort of like balancing the loss functions around large and small objects. So the typical architecture for object detection defines something what is called anchors, and they are like very densely placed in every location, which means we have like more than 20,000 of them. And if in this anchor we found object, we classify the anchor as positive, as like we just do classification. So if you have like large objects like this car, you can see that there will be a lot of anchors, and this is kind of the standard. If you have small object, you will find only maybe single anchor around them. And these anchors are usually like equally placed along the grid. So this is why if this is small object, you move this anchor by few pixels, you actually already like missing the object. For the large ones, if you move the large anchor like few pixels away, you still overlap a lot with the object. So our idea was kind of to try to like replicate many of the small objects, and it didn't really, I would say, work well. We improved a little bit, but like we also got much worse on the large ones. And I wanted to say about like other, I would say 2-3 papers from the last year that I think are like very important in this topic. So in SNP paper, they also noticed that a lot of, so we see here like 2 data sets, ImageNet, the blue one, and distribution of boxes in COCO. So in ImageNet, most of the objects are actually quite large. In COCO dataset, like between like 90% of objects are on half size of the image, and and around 10% of the smaller objects are just like 0.2%, like 0.2 of the whole image. So if you have to force your detector to learn objects on such a range scales, maybe this is one of the problems in this framework. And at least a few years ago, we were thinking, okay, this is true that as humans, we actually focus in different location, we analyze, and then we go to the next one. In neural networks, we don't have to do that because actually we use convolutions, and they analyze the grid in the same way. So why there would be a reason to try to focus in specific location? And there were few papers from like people who were working on this topic, trying to dynamically with reinforcement learning jump to like locations that are like of high value, of like high potential with the objects, but I think it was like over-engineered that time. And SNP and sniper ideas are kind of simple implementation that try to like manage that. And here is like example from this paper shows that, okay, if we have like our standard architecture and we start from 1600 by 1600 image, and we get to the last, let's say, block of ResNet, where it will be 32 by 32 times smaller. For large object, you will see something like that, but for the small one object, you are like never going to find it. So now try to design classifier that is able somehow find this guy and this guy at the same time may be difficult from the last features. So they did this relatively simple experiment, trying to like somehow force detector to like look at the same size objects. And in the first experiment, they actually just applied the standard training with like you detectors take quite a lot of memory, because you have like many layers of convolution. You usually also use patch normalization, blah blah blah, which means like you cannot really train on very high resolution images. In the inference time, because you only do forward pass, you do not need to store all the intermediate tensors. Therefore, to exploit this opportunity with additional memory, you usually take like larger image for the inference. So this experiment refers to these two columns, which says, okay, if we train on images of size 800 and we try to do inference on images 1400, we see that our performance is 19.6. And obviously, if we train on 1400 and we do inference on 1400, our performance is better. But maybe surprisingly, is not a lot better. It's actually a little bit better. So that's something that can be already questioned. When you train on multi-scale training, like defined in this column, when you sometimes give your network like smaller image, just to kind of force it to look at the smaller objects, and sometimes give like larger image, and potentially these tests are done on like small networks, so you can fit probably 1400 by 1400 image during training. You see that you still gain similar performance. This experiment actually tried to like only keep the objects on the large images that are smaller than 80 by 80 pixels, which means like you may take like large. So one of the hypotheses is, okay, maybe if we train like too large images, we actually are overfitting too much to large object, because there is a lot of anchors inside the network that match with that large one. So maybe we will remove them and try to train only on small ones. That also wasn't too good idea. But something that is in this direction and was actually a very good idea is to try to capture parts of the image, but on different scales. So you can look that actually all these three guys are now cut in the way that they have similar size. And is done actually in relatively simple way. So they define like 3 scales on which they will train images. They define images in the scale between 1400 and 2000, between 800 and 1200, and between 488 and 100. And on these 3 scales, if there is like object that matches one of these range sizes, which are like adapted. So on very large image, we just want to look for like small objects. On medium-sized image, we want to search for like medium-sized objects. And for small images, we want to only search for large objects. With that, they are actually received like much better results, at least in this one experiment. And there is like few tricky details. So because you may found like that there is like a lot of anchors that kind of fit into like parts of your ground truth, then you also have to remove it. But these are like details that you can easily, let's say, implement. So with that idea, is like, okay, so we are doing like 3 detectors on 3 different scales, and then we just combine all these different object sizes found on them, and yeah, that actually improved quite a bit. So I would say that the experiment that is worth looking at is this one. They use like DPN network, doesn't really matter. They get to like 45.7. I would say when we were fighting back when I was in Google, we were actually like spending thousands of GPU on getting to train this Coco data set, and we were getting to numbers like on the level of 35. Kind of like this simple experiment. So like and it was in 2016. So in 2 years, like this is really, really huge progress. And yes, I think this paper is worth checking. And the follow-up of this paper that also happened last year about like even smarter sampling of boxes of these views. So against trying to like randomly find the patches that contain specific box sizes, they do this in, I would say, greedy, smarter way to just find all the positive boxes greedily and try to, okay, so let's maybe have a look. So the yellow, maybe red box is the smallest one. So in red box, like all the detections that we have will be trained. But for example, in the purple box, which is like large one, we actually omit the red ones are the ones that will be ignored. We don't care about these small objects. We just train this this part for like relatively same size boxes. And obviously, if you sample from like positive examples, like here, you also have to make the way to sample negative examples. So I think what was really smart is to use the same region proposal network, which is like the first part of the network that proposes where to look, and they train like for 2 epochs just the model on the positive examples, and then after 2 epochs they start to use region proposal network to search for examples where they perceive that they found something and use them as negative crops in the training as here above. So with this simple strategy of like not trying to maybe do reinforcement learning with some sort of cues where to look at, but actually just simple sampling of like where you see boxes and where my model is wrong. So for example, here they perceive that, okay, there may be something, so they just take this chip to the training dataset. So now we have like only 512 by 512 chips. We do not have to train on larger batch, which is perfect, because now you can take advantage of batch normalization. So one of the trends was also to get batch normalization to work on like small batches. And there were a few papers that tried to do this. One was like batch renormalization or instance norm, group norm. These are like papers that try to give you the same advantage of batch normalization, but for small batches when your statistics are not so accurate. So with this like simple strategy, they actually have currently state-of-the-art results on the Coco dataset. And they do not use any like typical tricks with like oversampling of negative positive anchors. They just train on these 3 different scales. Obviously they use like tricks that were developed over like a few last years, like soft NMS. I think they also use deformable convolutions. So there is like few advances that happen in 2016 and 17 that are used in this paper. What is interesting, they also were able to train it only in 14 hours on 8 GPUs, which actually, like if you think about 28 hours on 4 GPUs, it's not so long. And yeah, these are results. How much more time? Okay, I should finish. Okay, so there is like one more paper that is worth mentioning, but I think Sniper is the most important to remember if you care about object detection today. M2D, that is like alternative that is much faster, but also very good. And one word about Tensorflight, like all we care is actually object detection. These are like some samples of our system, like more than like almost 2 years ago when we were like focusing on general aerial views. Nowadays we use object detection and instance segmentation to understand buildings for insurance companies, and this is like core of the technology that we are developing. And yes, if anyone is interested to speak, please reach out to us. Thank you.
Okay, thank you, Zbigniew. Questions? No questions this time.
Perfect.
Okay, so maybe later during networking. Thank you once again. Adam.
Okay, it works. All right, so thanks a lot for coming, and thanks a lot for the invite to give this talk. So my name is Adam Paszke. I'm part of the core team of PyTorch. I've been with the project since the very beginning, and recently we've hit a pretty major milestone, which is the 1.0 release, which is kind of to send a signal that we've reached a stable point where people can actually start building like bigger applications on top of our software. So just to get an idea if I have to cover the basics or if I can just skip to I don't have a lot of time, so the more time we have for the new stuff, the better. So how many of you actually know PyTorch? You don't need to know exactly the APIs. It's like everything you need to know for the sake of this presentation is just like what PyTorch is and like what you could actually do with the library. So if you could please raise a hand if you know PyTorch. All right, so it's pretty much almost everyone. In general, if you don't know, I'll just do a 30-second intro, I guess. Most generally it's a deep learning framework. You can think of it just like TensorFlow. At a simplest level, it is actually kind of more like NumPy. NumPy is this multi-dimensional array library in Python that lets you do a lot of those operations on those arrays. And at the lowest level, PyTorch is exactly the same, except obviously we have some nicer features which are not supported in NumPy because just redoing the same work would be just stupid. So first and foremost, we do integrate with NumPy very well. So you pretty much get we have methods to convert arrays in one direction and in the other direction. Basically, it's really cheap. There is no memory copying happening. So if you modify the torch array, the NumPy array changes. If you change the NumPy array, the torch array changes. So we're basically just reallocating descriptors to the data in memory. But you can use torch as part of your application or as part of a larger application that uses NumPy today. But in this single function, you can just convert the inputs to PyTorch for free at the beginning and then just convert back to NumPy at the end of the function, and you're free to kind of use the nice features that I'll just quickly talk about right now. So one of the most important ones, especially for machine learning, that's something that enabled the whole boom of neural networks, is accelerator support. So pretty much everyone today does when you do research or even inference usually. You will use, if you have a larger network, you usually use a GPU, and that's because this array-oriented kind of programming paradigm basically fits the architecture of the hardware of GPUs very well. They're just simple kind of processing units which can do thousands of mathematical operations, only mathematical operations. There's no complex instructions really, but just the sheer throughput kind of trumps what you can do on the CPU in a given amount of time, even though it like sometime, anyway. Yeah, generally the API is like really easy to use in this case. So like in here we just allocate two arrays, we add them and print. All of this is happening on the CPU just as if you were using NumPy. If you want to use GPU, there are two ways. So first, if you construct an array in Torch, you can specify the device argument. If you kind of want to convert an array that, as I mentioned, like you got it as an argument to a function, there is the to method that lets you like kind of change the device where the actual data lives. And then all the APIs are the same. So like if you add them, it's still the plus. If you all the functions for like matrix multiplies, convolutions, all of those are like completely generic over where your data lives. They will like dispatch to the correct device automatically. And the like top line is really nice in this case because this means that basically if you have a CUDA GPU in your computer, we'll use this to do the compute. But if you don't have it, we'll just use the CPU. So like you can you can try out your scripts on your laptop. You can kind of debug them on your laptop. And once you like run them on some smaller examples, and once you're confident in your script, you basically send it to like a more powerful server, and it will automatically start using GPUs in that case. So that ends up being really convenient. And another really crucial feature for machine learning really is to have very high performance automatic differentiation. So machine learning ultimately is all about mostly about gradient-based optimization, right? I won't be getting into details how this works. The important part is that PyTorch can actually differentiate, like no matter what code you write in Python, no matter what language features you use, if the function that your program implements is differentiable, so like neural networks are pretty much always differentiable, so it doesn't matter how you implement them. The important part is that we can actually compute all the gradients. So we do support usually differentiation of scalar functions, which is the most important case for machine learning. But you can also do like Jacobian vector products, Hessian vector products. If that's what you need, you can also do this. So in this case, we're not using any complicated language features. We do have this polynomial function, and basically the API is you have this single function like torch autograd grad, which you give it the the output of your function, and you give it a list, or in this case a single input to this function which you want to compute the gradients with respect to, and that will just return the the gradients as a list. You can kind of print them, verify that they match, and all this. All right, so that's like a quick intro for those of you who don't know PyTorch. So hopefully, like it's just like kind of TensorFlow crossed with NumPy. You can think of it that way. So yeah, but like as I mentioned, the important thing right now is that we've actually hit this milestone, which was really important for us because like it was actually not such a long time. I think we've released the library like 2 years ago. It was January 2 years ago. So a lot of people actually started building applications around it, and it like gained some traction in research. But a lot of people had kind of were like wondering if that's actually like a good choice of a library, if you wanted to like actually deploy some applications and actually like serve some customers, if it's just a research thing, or if you can actually like start using this in the industry somewhere. So the kind of main idea behind this was that yes, we're kind of stable, and like we want to enable a fast path because like we kind of had some attention in the researcher community in the academia. Now we want to enable kind of easy transition from the research part, which is very important in machine learning. Ultimately, like if you're doing some kind of, even if you're doing Kaggle competitions, whatever, like you will be iterating on an idea. So the important part is that you should be able to change your program very quickly because you will be trying very different things until you actually get to something that works. And only this single thing that actually you verify that the product of all of those iterations, this is something you will ultimately want to deploy. So I think those are like the needs for research and for deployment are kind of at odds in here. And so we've been kind of serving the first thing, but now we kind of want to enable easier transition from one to the other. Although it is really important to kind of understand what do I mean by deployment in here, because like people even prior to 1.0, people have been running PyTorch in production, and that was like usually completely fine. Like I knew companies that did this, that actually deployed this even to embedded devices. Like there are some cases where, like ultimately Python is a language which is basically kind of two main use cases for it right now are either, you know, data science, machine learning, or web servers. So a lot of people actually are using Python in production, and even like really big companies. So if this is like kind of your use case, you really don't like you could have already you could have already done this. The like only cases where like people actually had problems with using their Torch models was mostly either when you want to deploy to mobile devices, because you probably don't want to run like the full Python interpreter. Python is not like a great language to run on mobile devices. It has like a pretty heavy interpreter, so like it increases like mobile app sizes, and it's not very optimized. So like probably not the best choice. The other thing, you know, PyTorch is also used at some like really big companies. Like it's supported mostly by Facebook, but it's also used like at NVIDIA, at Uber, and so like they're serving a lot of customers. So basically for them, if you can somehow cut down on the costs of deploying this, like Python is probably fine, but still, like if you have a more optimized runtime, you might really save like on the amount of servers you need to run the application, or like on the power that actually like your data center uses. So the kind of mode that you know today, this is called kind of eager mode. So this will stay the primary interface to PyTorch. You basically the most important thing, we started with this, and the most important thing, as I mentioned, is that it's easy to write and debug and edit, because those are the things you actually need when you're working and building like a new application. The problem is that in this sense of deploy that I just defined, kind of, it is really hard to do this. So basically, the way that we came up with to kind of address this, because ultimately you want to get rid of Python, but we don't want you to kind of throw away your Python code. So we've added something that's called script mode. So script mode effectively is a new programming language, although you really don't need to be afraid of it because the syntax and the semantics match Python exactly. So it's kind of like a clone of Python, except you only have access to like a subset of all the features in Python. So like we've kind of eliminated a lot of the dynamic behaviors from Python that let us like run more complex static analysis on your code, like actually derive types for things, and this is something that enables us to either optimize your code to like understand the structure of your network and of the computation that you're doing, and like possibly generate machine code for like a number of operations instead of kind of running them separately, as we would have to do in eager mode. And also the other benefit is that starting from 1.0, we also have a C++ library that it's called libtorch, which you can basically link into your application. So that's kind of a lightweight. It contains pretty much everything that PyTorch does, except it doesn't bundle the Python front end, and it actually can run without Python completely. It like even has autograd and all this. I'll get to this later, but basically this is something you can actually start linking to like embedded programs or mobile apps, and like using script mode, you can like export a format that will be later loadable into such app if you just link the library. So importantly, the subset of the language that we support today, those are mostly tensors, scalars, scalar values, basic control flows, so conditionals, and loops. You can print things. You can have strings. You can have tuples of anything, or like polymorphic lists, or even nested lists are fine. And you can call other functions. So it's really not like a lot. You can't really define classes, for example. But this is really like ultimately most. Well, there is some limited support, but anyway, this is like most of the language that you actually need and that you actually use like in day-to-day PyTorch programs that we see in our like looking at what our users do. This is pretty much everything that they need to implement their own networks. So, okay, again, another problem is how do you actually transition your eager program to a script program that can be exported or optimized? And there are basically two pathways you can take. So the first one is tracing, and the other one is just using the script directly. So tracing is kind of, let's say, the simpler way because it actually doesn't even enforce the subset of Python that I mentioned on you. But but it also like comes with some downsides. So we're not actually doing any static analysis in this case. It's like you give us the function that defines your model, and you give us example input, and we'll run the function once, and we'll kind of record the list of like calls to PyTorch. So like if you did some convolutions, if you added some tensors, we'll kind of recover the data flow of the tensor only data flow of the function. But if you had any like conditionals or if you had loops, it's fine to have them. But we won't really be checking like if they would run, like if you pass a different input and your program normally would execute a loop a different number of times or would take a different branch in the conditional, we won't even check the condition again. We will basically like take the branch that was taken in this particular example. So, and like we have some warnings to kind of help you determine if like you haven't messed up something when you use tracing, but it is really your responsibility to kind of understand that like the data flow graph of the program has to be fixed. So this seems kind of dangerous and constrained, but you know, basically one of the most popular models, like convolutional neural networks, usually just looks somewhat like this. So the data flow graph that you actually care about exporting is kind of fixed at every particular iteration, right? So in this, this is like the perfect candidate for tracing because like you don't even need to edit your program. You just like trace it and that's everything you have to do, right? So, you know, so just to kind of reiterate, if I were to implement a model like this, those like an nconf to d, I won't be getting into the details of the API, but you can think of them as those like boxes in here. So those are kind of the layers of the network. And I would just kind of loop over, obviously it's like a simplified example, it's not exactly what it was previously, but I would just probably loop over them in this fashion, right? So I have a loop, but again, this is perfectly traceable because, you know, the list of modules, like the length of this kind of path might, you know, change depending on some command line parameters. But, you know, the kind of once you define your model at the beginning of your program, you could still safely trace it and later use the like, you know, function that was returned from trace that will mimic the behavior of this model because this list of convolutions will probably stay constant over the execution, so over the training. And so like a program like this, which will be seen kind of by trace, would be completely equivalent in this case. And in particular, we have a Torch Vision package that implements like the most popular, you know, computer vision models. So if you take pretty much any model from there, you should be able to trace it safely because they're all like models that don't really utilize control flow in any like, you know, data-dependent fashion, let's say. For script, that's like another version. So again, now in this case, you are actually restricted to the subset that I mentioned. Script is like a function annotation, so you put it before the definition of your function. But the benefit is that we actually do static analysis on the Python source. So we will correctly recover control flow from your program. And like it's still a Python program that like lives in the same file as like your all other Python functions. And if you know, if you kind of escape the subset, if there's something we can't understand or we can't prove this is safe to actually translate it into Torch script, this will just become a hard error. So like you will at least know that the program would change the semantics. But if this actually succeeds, you like should see completely no difference in like how your program runs if with this annotation or without it. So kind of the most common example for which I would use script is like recurrent neural networks. So in this case, like if you're translating, I don't know, sentences in one language to another language, you will probably have like a for loop like in this function, which like runs over some, you know, sequence length in this case. And you don't really want to like unroll this loop for like, you know, the number of iterations that it took on some example inputs. You actually want to have the clear dependence on the size of this dimension embedded in your program so that every time you kind of execute it, you will look this up again. And so script will do this, script will see this, and in fact, this is perfectly scriptable. Also, scripted functions require type annotations. We do support, you know, the Python 3 syntax. There is some kind of a, let's say, polyfill that's like a standard thing of annotating in Python 2. We also do support this if you use this for some reason, because we will actually be inferring types. You don't need to like annotate types of intermediate variables. We will be actually running type inference on this code. So this is actually why we need this. And the important part is that they actually mix. So you can use scripted functions while tracing, or you can or like your scripted functions, I mentioned they support function calls. You can call things that have been traced before. And most importantly, scripted functions also allow you to call back to Python. So, if we had a function like this, but somewhere in the middle, like, we would reference some other function and we would just call it, but it wouldn't have this annotation at the top, that's still perfectly allowed. Obviously, like, if you have a program that has references to Python functions, you can't really export it because there is no way to actually run this without the Python interpreter, so that kind of misses the point. But we can, for example, optimize such a program, and most importantly, this allows you to kind of add those annotations function by function. You can run your tests in between, so you can kind of verify that everything works as expected. And also, like, if you actually have a model that you deployed once, and then you want to go back to the research cycle, you can still like eliminate some of those. You kind of, I don't know, you want to use NumPy and some, or like some external libraries in some functions. This is not something you can do in scripted functions. You can just like remove those annotations in a few places, and your program will still continue running as like it usually should run. And yeah, and as I mentioned, we have a like new library, a new interface in C++. So like in one line, basically there is this torch.jit load thing. You specify the path to the file, and this loads a completely executable model. So in this case, if we export like a ResNet, we just like we just generate some random data for it. We call forward, that computes the model, and we get the tensor back, and that's it. Another important thing is that we can actually optimize some of your use cases. So basically, the roadblock sign in here is kind of because we didn't actually spend so much time on this, so it's not like I'm not promising you right now that you will do wonders in your networks and like we won't miss any optimization opportunities. This is like kind of an early stage. We've been mostly working on getting the script to be like robust and give nice error messages and like be kind of hard to break. This is something we're working on now, so this will be getting better over time. But basically, the idea is that if you like use a vanilla LSTM network, let's say, which kind of maps well to like what NVIDIA cuDNN library allows us to do, you will like go really fast. But if you implement exactly the same network using like in Python using our API, your perf drops basically like 5 times. So it's a pretty significant difference. And so Script kind of aims to eliminate this gap. So if we take like an LSTM variant, we can already, just by adding those annotations, which is like just a few minutes of work really in this particular case, in one benchmark we're tracking is like a 3.5x speed up per iteration. So this is like doing some loop optimizations. This is generating native code for like GPUs to actually execute your network more efficiently. So there is some, there are some things we're doing there to kind of improve on that. Apart from this, something that we've released, so C++ extensions have been there. This is like a way to interface with Python. I don't think I'll have time to cover this today. I'll just go straight to the interface. So this is in beta. Interface is in beta. Basically what we did is some people actually don't want to use Python even for training. Like if you're doing some RL research, like if you're doing robotics, maybe you might have like a C++ program that controls the robot, because like the producer kind of bundles only C++ libraries for this. Or like if you're doing RL in games, some games like StarCraft only have like C APIs to kind of interface with them, and you like should go really fast, and you have a like low latency environment. This is why like we kind of replicated everything we have in Python, but in C++. So I'll skip the extensions. Basically that like allows you to really quickly bind your C++ code to Python if that's what you want. But just to kind of give you an idea of how the interface looks like just to kind of show you that it's really similar, that's like how you would define a simple like 2-layer neural network in Python, and that's how it looks in C++. So like you can see that there's a lot of correspondence between them. If you take a look at like the training loop, that's like an example training loop written out in Python. If you were to translate this to C++, that would look like this. So it's like a basically line to line exactly corresponds. It's just that like the syntax of C++ is slightly different, so you just need to sprinkle some braces, and everything works. It's like template free, so compiler error messages are relatively sane. So yeah, you might actually try using it if without feeling super brave. So. And many things are there, although as I mentioned, this is in beta, so there can be breaking changes to this. You can try this out. If you pin like a particular version, obviously this won't break, but like if you later update, this might be slightly changing. So definitely like, we'll notify when this will be fully ready and fully stable. Right now you can actually play with this. A lot of people are actually using this even today. But do it at your own risk. But like things like helpers for neural networks, for optimization, for serialization, and for the JIT is the script is kind of it works as a just-in-time compiler for models, so that's why it's called this way. Finally, there are some distributed improvements in 1.0. So most importantly, there's some new abstractions that like allow you to run a lot of the operations asynchronously. So you can like interleave a lot more data transfers and actually make it much more efficient than it used to be. You can have like independent groups, meaning that you can use different backends to send different data. So like if you have CPU tensors, you might want to use one library. If you have GPU tensors, you might want to use like Nickel from NVIDIA or some other library to actually send them because they're more optimized towards those use cases. So now you can do this. There are some performance improvements. And another really cool thing is that we actually right now you can actually implement programs that are fault tolerant. Previously, like if a single node would fail, the whole training would kind of go down. Now you can actually recover from this. And also that allows you to like implement elastic sizing. So like if you can kind of track the price of on-spot instances, if it goes down, you can spin up more instances, kind of restart the distributed communication and like actually, drive the speed of your training by the prices, let's say, of compute power in the cloud. Yeah, just to kind of end on another note, if you're tracking PyTorch info like news, we are merging PyTorch with Cafe2. So PyTorch will basically remain. Cafe2 is like another framework that's used at Facebook a lot, mostly for inference. There's like a lot of good people working on it who like have a lot of experience with actual inference at large scale. And so basically we're kind of joining efforts with them. PyTorch and JIT will kind of be the front-end part to it, but we're like merging a lot of what's been built in Cafe2 over the years to kind of also speed up to improve the inference performance in PyTorch today. And yeah, that's pretty much all I have today. So as I mentioned, there's like a core group obviously to PyTorch development, but it's like a fully open source project. There's like no code is actually hidden. All development is like happening on GitHub. Like every single patch that goes in goes through a GitHub pull request. We do have like collaborators who are completely independent. So you're very welcome to contribute if you'd like to. But it is supported by like some large entities. Like Facebook's kind of the main driver, but there is also NVIDIA, Salesforce using it. Uber is also kind of increasingly. They have a really cool kind of probabilistic programming language built on top of PyTorch. So if that's what you're into, you should also check it out. And yeah, and basically a lot of universities, Stanford, the deep learning course at Stanford is in PyTorch this year, I think. And so yeah, it's definitely like a growing thing. We're like super amazed by the community and we're very thankful for this. And yeah, that's basically where the things are at today. And thanks for coming. And that's it.
Okay, thank you, Adam. Any questions to Adam?
Hi. Do you plan on actively supporting AMD GPUs?
Yes, there's some work happening on this. Actually, like we're even tracking, like we were even working with AMD on that. So it's kind of we're not distributing AMD packages, but there is like a way to build. I think it's like described in some documents, like in the wiki, I think, how you can do this. We're actually even tracking the AMD build, which is, I think it has pretty much complete coverage of our ops. We're even tracking this in like our continuous integration, so like no pull request is kind of allowed to even break this build. So they're definitely working on adding this. So it's still kind of in the shadow, but it is definitely getting to like being very usable right now. So there is some work happening on that.
Okay, thanks. Any more questions?
What is actually the speed up when you move from Python to C++ with the bindings? Can you share some insights on that?
Yeah, that's a good question. That definitely depends a lot on your model. So if your model is like ResNet 50, it's not like Python is actually slowing it down. It has like very few operations, and most of them are extremely like expensive. Convolutions are super expensive, basically. So for ResNet, I would expect like completely zero speed up. Basically, what improves usually performance is when your models are very small. You have like very small arrays. You're doing very simple operations. So like you're mostly kind of doing pointwise operations probably. So usually like some NLP models see speedups if you move them. Usually vision models see no speedups if you move them. That's kind of the rough, let's say, rule. But obviously there are exceptions, and a lot actually depends on the program. Sometimes Python is a problem. Usually Python is not such a huge problem. So it really depends on benchmarking. I can explain later, like more later. It's kind of technical, but I'm not sure if like now's a good time to do so.
Okay, thank you. Still have time for one more question. Yes.
Hi, thanks for the talk. And I wanted to ask, so for the 1.0, the JIT was kind of the core focus that you were like advertising. And do you have anything to say about what are the main future directions, thinking about, for example, what PyTorch 2.0 will be? Or currently you're just focusing on like expanding the Python coverage for JIT and making it more optimized?
Yeah, that's also a good question. Although I don't have a very good answer. We're still kind of in like 1.0 hangover. Let's say that was kind of a brutal sprint at some points to actually get it working on time. So I think for the JIT at least, most of the things we'll be doing right now is either expanding the language features that we support, because I think there are still some things that are relatively fundamental that are missing and that I'd like to see there. Also definitely more resources will be devoted to performance optimization, because that's something we, as I mentioned, we kind of worked on for, let's say, RNNs, but we kind of only skimmed over other models and we didn't like pay a lot of attention to them. So I definitely know of like some optimizations that convolutional neural network can benefit from that like I've been working on. I have open PRs for them. They're not finished just yet, but like in the future it should get better. So those are probably the main directions. From the rest, most people are like working on unifying Cafe2 and PyTorch. That's like a huge effort, and that will also yield some nice speed ups hopefully and like clear up the architecture a bit. So
Nice. Thanks, Adam.
yep, thanks a lot.
Yeah, thanks once again. Okay, so you will have opportunity to ask Adam and our other speakers more questions during the networking part, which will start soon. But now, just I will give a few closing words. So, okay, yeah. So, thank you once again for coming and joining us today. And I know that most of you are already members of our Facebook group of Warsaw.ai. Some of you already follow our YouTube channel. If you don't do it, if you haven't subscribed, then you can do that. And if you have any questions or remarks or ideas what we can do better, how we can improve, then you can always send us feedback by email as well. Okay, so at the end we would like to thanks once again to our sponsor, deepsense.ai. Thanks to them we also will have this networking part at the end. And I would also like to announce the expected date of the next meetup, the next event. It will be probably 4th of April. So of course there will be a separate announcement in the future. But yeah, that's the tentative date which will be confirmed later. All right, so thank you once again for the attention, and we invite you for the food and networking. Thanks.